Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, one of our best students, may I say. His name is Girish Kumar, and he's been working on a couple of courses for ROS2, for the ROS2 Basics in C++ and in Python. He's been working on those two courses, so he's ready to show us his final project. So without further ado, hello Girish, how are you? Welcome back. How are you doing?
Hi all. Hi Rodrigo. How are you? I'm doing fine. How are you?
Great, I'm doing great. I'm excited to see what you've come up for your project. So whenever you're ready, you can start sharing your screen and show us what you've done with your ROS2 Basics courses.
Sure. And by the way, nice to meet you again
Nice to meet you again. Let me
after Ross
allow your
one
share.
video. So let me start sharing my screen. All right. This one. Share. All right. So this is the page where I connect with the remote lab. Apparently, I have not connected it yet. So let's just wait a couple of minutes for it to get connected.
Okay, you are connected to the robot, right? You're connecting?
Yes, I am connecting to the robot right now. I wasn't connected before. I had temporarily disconnected. Now I'm connecting back again. Alright, so let's have some basic setups done before we start our run. And since this robot is running on ROS1, we need to start ROS bridge, and those ROS bridge uh, functions I have actually written into a bash file. So I'm just going to start the bash file, which will start the ROS bridge connection.
Yeah, good idea.
Because it's like 4 command lines and I need to copy paste, and this is just a hassle, so I just put it in a bash file.
Mm-hmm.
All right, so uh, yeah, ROS bridge is ready. Now we just need to have another window running ROS1 source. We need to have ROS1 source on another one window. So source dot dash rc ROS1. All right, so this is just to make sure the robot is, since the robot is running on ROS1, we just need to have one of the terminals running ROS1 in case robot goes haywire, and we can just stop it.
I see. Good idea.
So robot is responding. Oh, that shouldn't matter. Right. Turn a little bit. Go down. All right, that is a good spot to start. All right, the next thing what we're going to do is turn a little bit. Before that, we need to launch RViz. So just to see what is happening. So
Mm-hmm.
RViz 2, ROS2,
And you also make sure
and
this
then
way that the
I
bridge
have
is
my
working.
I have my configuration preloaded, so I'm just going to open my config as is. So user ROS2 source base config describe. All right, so this is the current position of the robot, and the big red arrow mark indicates the odometry, the
Uh-huh.
heading of the robot, where the side direction it's facing. And this red color field is basically the laser scan output, or say the points that the lidar, which is positioned on top of the robot, is acquiring. So this is basically the arena itself. And let's just minimize that and have it in the bottom. All right, so now we are set. So first I'm going to show you Python. So now that everything is fine, ROS2 launch RCL Pi Basics project main tab main.launch.py. So this one starts my Python version of the program. So let's just start it.
Mm-hmm.
All right, so the program is initialized, and as a first step, it's actually heading towards the wall. So basically, it's finding the wall and trying to face the wall. So as you can see, the robot is rotating. As you can see, uh, these two. Is my cursor visible?
Yes, it is.
All right, so now as you can see, it has found the wall and it's moving towards the wall. Now it's moving closer to the wall. And now it has stopped in front of the wall, and now it's aligning itself with the wall so that to start the wall follower algorithm. So now it is pushing looks close to the wall, and right now, as you can see, uh, where is it? All right, so this run is actually not good, so let's just stop that and then restart because
Why is
for
that?
some reason the first run doesn't actually work, and I've tried that several times before, and
Huh.
that seems to have some anomalies. So let's just come back a little bit. Position it again. Come back. Okay. A little bit front. So let's try it again. Python. So it's heading towards the wall. All right, now it's found the wall and it's moving closer to the wall.
And how'd you figure out that it wasn't going to work that first time?
Because my action server returned the result prematurely, so I
Oh,
knew it's not going to work.
right.
So now it has started working, and again, this time it again had the problem. So yeah, my action server has prematurely ended, so it says finalize goal callback. So this is probably there's a issue, so we should probably come in a little bit back and start again into open space.
And what if you just let it go? It'll just run into the wall because it thinks the action server's done?
Yeah, so basically it has to start in a way that it has a lot of space in front, and sometimes the robot doesn't start that way, and that is what causes the action server to finish prematurely. And I haven't found a proper way to fix it. So
Hmm.
because I don't have much time, this session the session does not allocate you much time working on the robot, so I
True.
wasn't able to exactly look into that points deeper. So I'm hoping this time it should run. All right, so the starting position doesn't matter in my code, but the problem is in the real robot, it seems to be a problem. It doesn't happen with the simulation. You can start it from anywhere and it will end up in the right place. But only in case of simulation due to external factors like environmental lighting or probably just the way it is located, the arena, it seems to have some issues. And due to also the fact that the sensors.
Yeah,
So
so
now it started,
it could be a couple things. We'll talk about
and
them.
okay, it seems to be, we still have an issue there. All right, so let's just come back. Let's just come way back.
That's very
All right,
strange,
so
though.
this is another good place to start.
Hmm.
I'm hoping this time it should work because it's one of the places where it works fine. So hoping it should start well. All right, moving closer to the wall. So the only problem here is it should position itself with a wide area in the front. If it doesn't, then that is a problem. So that's one of the drawbacks of the algorithm that I'm having because it is I need more heuristics, and this doesn't give much. And we actually have a go. So
Nice.
yes, now it's everything's working fine. The action server is responding fine, and we have a good run. So as you can see, the robot has started moving, and just for a while, and yeah, let us just see the instantaneous distance that it gives. So the current
Hmm.
total is the distance moved. So at this instant, it has moved this much meters. So this keeps accumulating, and you get this cumulative response from the action server. So let's just reload ROS2 meanwhile. Okay, so we receive feedback from this one. We'll just maximize this. Reload the configuration. User
Just a tip.
ROS
You can do
SRC.
arvis minus D and then find your configuration.
Oh,
Just a tip.
I actually did not know. Thanks
Uh,
for clarifying that. Okay, for some reason ROS keeps closing. I don't know why.
that's fine.
Okay,
That's fine.
so
We saw it earlier, so we
okay,
understand
let's
what
just.
you're.
All right. So the good news is the robot is still proceeding, and it's going to take about 3 minutes to complete a run. So let's just keep looking because it's going to stop eventually at the exact spot where it started. So you'll be able to notice that in the post processing of this lab
Uh
once it
huh.
is done. So in my program, I've actually added a method to record all the odometry and put it into a file and give you the distance covered as well as the speed, the average speed for the entire lap, as
Oh,
well as
nice.
time taken for the lap. So we would be able to see the statistics of this lap once the lap completes. And it should be completing soon. So it's okay. There we go. So the ORAN results are out, and it is starting the procedure again. So you're going to stop it. So Control C. All right. So now we cross-verify the output. So CD ROS2 SRC. So this is Python. So RCL Py extra, and here I have a Python code to generate the the odometry value. So odometry plotter. That's gonna load. Yeah, there we go.
Oh.
So here we have the entire lap that we can see. So just to cross verify with what we have done. So here is the ODOM results. So we can see it has covered 5.6 meters. So that is 5.607 meters. And then we have 132 seconds of run. So 132 seconds and
Uh-huh.
0.042 meters per second, which is the average speed, 0.042 meters per second. So here what you see is the entire plots of the odometry. And then the red box denotes the landmark zone. This is one of the concepts that I use to understand where the robot is, and
Mm-hmm.
it has come closer to the start position. And there is also a place in my code where I set the distance between the start position and the final position once it has come into the landmark zone to be the minimum. So this is apparently not a good run, but another run would probably fix this. So yeah, for the time being, this is the output of the Python's run. So
I
the
mean,
good
it
news is it's
satisfies
within
the
the
landmark.
box where it started. And as you can visually see, we started from here and it actually ended over here. So that's a perfect run
Yeah.
uh, from what you see in the picture. The only thing it didn't satisfy is to have a distance from the start to the end to be the minimal distance, but that's fine given the actual considerations of environment and the arena setting and all this stuff. So now that our Python version is complete, we can go into our C++ version. So clear, and now we're going to launch the C++ version. So RCL5 becomes actually TPP. And then before that, we'll just clear up these ones. So CD, clear, and then we'll go to this one. So let's just position the robot again. So just to make sure that it doesn't have any problems that we saw earlier.
Mm-hmm.
All right, so okay, there we go. That's too much. A little bit. All right, there we go. A little bit front. Okay, this is a good position to start. One of the tested positions where I can start. So, all right, so let's start C++. So it's pretty much the same logic. So it's going to do the same. It's heading towards the wall right now. Okay, so it has found that the orientation ahead is the smallest distance to the wall, so it's proceeding towards it. Probably this run might fail, but let's just hope it's going to work.
Seems like it got way too close.
Okay. The chances are this is going to fail, but let's just see what happens. All right, so it has completed its positioning, and now it's going to start running. So hopefully it doesn't stop earlier. All right, we are actually having a go.
Oh, it
That's a
got
good
out of the
sign.
way.
So
Yeah,
it started.
nice.
So the good news is I've never had a failure with C++ programming. So that's one
Really?
thing that all of you watching this video should learn, that every time I've finished my C++ program, it has never failed, but Python has. And I believe that the problem is because Python actually gets converted to C or C++, which then goes to the robot. So
Mm-hmm.
I think there's a lag of some sort happening there because the Python gets transcoded to C or C++ and then gets into the robot, to the machine code or the low-level code. So
That's really
yeah,
interesting.
so there is probably a delay there. So yeah, my C++ has never failed in the actual run, like this one, what you see right now.
Right.
So yeah, so
But it's
we're gonna have a
curious.
complete run. So
It's curious that you seem to have.
yes, what is that?
It's curious that you seem to have identified where the issue is,
Mm-hmm.
which is the action server. And I had some ideas that
Mm-hmm.
maybe it thinks it left the landmark zone and then came back in, and that's why it was stopping. But that's interesting that you say that it might be a lag thing because the C++ version never fails. Because it would be every time in
Yeah.
the action server?
Mm-hmm.
Huh.
Yeah, it's
That's
always the action server, which it's prematurely stops in Python. So yeah, actually the problem with my action server design is that it depends upon the starting and stopping of the robot. And it is I have actually given like a 2.5-second delay before the robot starts, and once the robot stops after 2.5 seconds, the action server finishes. So while it is in
right.
the landmark zone, and because of the nature of this robot that you see right now, it is stopping and moving, as opposed to what you would see in the simulation. It is not stopping and moving, but it's a smooth continuous move.
I think
So
this is because
that
of
is
the
probably what
rate
is
too.
causing the sorry, what is that?
Just if you publish with a higher rate, it won't stop.
All right, so now we can see that the goal is complete and it has spit out the results and it's starting over again. So let's just stop it.
Yeah.
So we've stopped it. So now we have the results and we can see all the odometry readings over here. So we're just not going to consider that. and we'll just go straight to the results. So this is where our results are. Let's just go plot it. So CD ROS2 SRC RCL CPD, because this time we are doing C++. So extras. So Python 3.odometry plotter. So yeah, there we go. So we can see in this image that it is barely inside the
Mm-hmm.
landmark zone, but here is something that we got to, which is interesting for us to notice, because okay, let's just cross verify the statistics first. So we have a run of 6.115 or 1.6.116 meters, which is 6.116 meters. We have 146 seconds of run, so 146 seconds of run,
Mm-hmm.
and then we have 0.0418, so the 0.042 meters per second because of rounding errors. So yeah, all right, so let's discuss a little bit about this. So you can see that the start and stop position are within the landmark zone,
Yes.
but this seem to be having a large distance, because as you can clearly see, the robot's path is not actually expected to come exactly to the starting point. If the robot has taken a turn like this, it would have met at the starting point. But since it has come this way, it is actually barely inside the uh, what is it, landmark zone, but it has finished it because the code has a my program has a little check where the distance, once the robot is about to complete the lap wherein it has entered the landmark zone,
Yeah.
if the distance between the start point and the current point is minimum, and and it keeps moving until the next point is greater than the minimum. So it
Ah, I
stops
see.
1 second after it gets the minimum value distance between the start point and the current end point. So so if you zoom in this one further, you will notice that, let's zoom in a little bit. So you will notice that the distance between this point and this point is the minimal, but it has moved a little bit more and stopped there because my program has understood that this point is the minimum, and that when it calculates the distance at this point, it is over than the minimum. It is greater than the minimum, so that's why it has stopped right here, and and it is an optimal zone because it is within the landmark zone. So this is an exceptional case, and this is what tells us that the path of the robot is not exactly deterministic, or it is actually probabilistic. So you cannot actually determine or say for sure that the robot is going to start and stop at the exact same point.
Right.
All right, so now we have finished both our Python and C++ versions, and the robot has successfully made a complete lap. As you can see, it started from this point, it has ended at this point, both with Python and C++. So let's just finish this up, and then yeah, let's just move on to my presentation. So all right, let's just close all these. All right, so we don't need this anymore, and it's time for presentation. So
All right.
let me open up my presentation quickly. So what's the presentation? Presentation. All right. So here's where all the explanation happens. So slideshow, second current slide. All right. So yes, this project video covers both my Python and C++, as you can see written on the title. So first, we need to say what we're working on. So the problem we have right now is that we need to program a robot using ROS2, which would perform wall following with the ability to automatically detect a nearby wall and orient itself towards it, navigate itself within the arena performing wall following, while recording the odometry all through its lab and all through the positions in the lab while it makes in the arena. And it should also avoid collision with walls or obstacles. So as you have already seen,
Mm-hmm.
the run did not encounter any obstacle hindrances or go into any collision course. So the parts of the project is actually three. So we have the topics, we have the services, and the actions. So the topics basically deals with publishers and subscribers available in ROS2 to communicate with the sensors and actuators and navigate the robot within the arena. It is a minimalistic necessities that you would need to make the robot move and just navigate itself. It is a simple code where you can make the robot just move, and it does not contain any AI in that.
Mm-hmm.
So services is the part of the code which uses client server model, and this we use this as a synchronous action to just make the robot locate itself closer to the wall every time it starts a lap. So wherever the robot is standing, it just orient itself towards the wall and starts running. And action, this is also a server client model, and we use this in this project. We use this to record the pose and orientation of the robot all the way through its lap course. And this project uses two custom messages for the service and action. As you can see, the find wall server has a blank request and a Boolean value to show if the wall is found. And for action, we have an empty goal. We just send it to the action server. And then the result is a list of odoms, which basically gives you the odometry values. And the feedback is a recurring total of the distance that the robot has moved through the lab. So the first find wall method actually has 4 steps, and the first step is to head towards the shortest ray, which is basically to orient itself towards the wall. So what it does is it performs a 360 scan, and it finds the shortest ray as the average of the smallest ray that has the most or maximum frequency of occurrence. So why this is done is because you might have an obstacle close to you, and since the obstacle is less in area of the
Yeah.
scan. So if the smallest object is very close to the robot, the robot would still orient itself towards the valid wall.
Oh, nice.
So yeah, it will just rotate towards the smallest ray so that the front aligns with the smallest ray range. So and it just loops over until the front ray is matched, or it just loops over until 15 seconds, because we just need to have it less tedious, and we just need it to stop soon. Next one we have is the next part is scan for valid wall, which is a part of the find wall service itself. So once it finds the shortest distance, it needs to validate if it's the wall or it's just facing an obstacle. So for that, we again do a 360-degree scan and then get the frontal 120 degrees of the ray. So it is the front ray plus or minus 60 degrees.
Mm-hmm.
And then we choose the direction to rotate by comparing the shortest ray range on either side of the front ray. So if the left side has the shortest ray, we rotate towards the left, and vice versa. If the right side has the shortest ray, we move towards the right. And then we keep scanning for the front to 120 degrees, and then we find the mean standard deviation to keeping track of the previous range and the standard deviation.
Yeah.
So we have found a valid wall once we hit the values, once we hit the criteria of mean being greater than standard deviation, which is over here,
Mm-hmm.
and the previous standard deviation is less than the current standard deviation, and the previous range, the frontal range, is less than the current front range. So once this criteria is satisfied, it is actually facing a wall. Uh, it is a valid wall. So this is the bare minimum algorithm that I could come up with by myself without the help of a camera. So you can't access the camera. So with just the laser scan, which is basically like a proximity sensor, this is the best you can do to identify a wall which is in front of you.
Yeah.
So once the loop is done, we just rotate in the opposite direction a little bit, just so that we don't overshoot our positioning. And then once the valid wall is found, it is just ahead. It is just in front of the robot. So here we have 4 situations where the robot would find the shortest ray, but it may or may not be a wall. So in this first case, you can see that the robot is actually facing an obstacle. The shortest distance is probably the corner of this obstacle, and we don't want the robot to run towards it. Similarly, in the second condition, the robot is actually facing a obstacle, but it's facing the face of the obstacle, which is the flat side. But this flat side is very short, so it still cannot be recognized as a wall because it's a
Mm-hmm.
flat region in front of the robot, but it's still not a wall. And this is the third case. So the robot is actually facing 2 obstacles, and it's actually facing right in the middle of the obstacle. So it still has the shortest ray in front of it, but it's still not a valid wall. And in this case, it's actually facing the wall, and it's not facing any obstacles. This is the wall right here. So this is the actual scenario that we want. And to compare these uh, readings as to how we can make use of the readings, we can see that in these diagrams. So the black dot in the center of all these diagrams is the robot, and it's actually facing towards the left always. So the green
The
area
green.
represents the plus or minus 60 degrees or 120 degrees of coverage in front of the robot, and it's in all the four cases. So in this first case, it's actually facing the obstacle, the corner obstacle, which you saw over here, the corner place. So it's actually facing the corner. And then you can see if you just plot the ranges in a Cartesian plane, you'll just get this kind of a graph. And the frontal 120 degrees is the green zone, which if we extrapolate as this in this way, we will find that the green line, which is basically the mean line, is between the highest values and the lowest values. The highest value is the red line, and the lowest value is the cyan line or the blue line, and the yellow line is standard deviation. So
Mm-hmm.
the mean line is actually between the maximum and minimum. And in this case, which is the facing the flat side of an obstacle but not a wall case, we still have the same design or the structure going on over here. We still face the same template of the mean being between the maximum and the minimum. And similarly, for the third case where it faces multiple obstacles in front of it, we still have a model which shows that the mean is between the maximum and the minimum. And in the fourth case, where is it? So in the fourth case is actually facing the wall. And in this case, what we have is the mean the mean still being between the maximum and minimum. But the point to note is the standard deviation line, which is the yellow line, is less than the minimum line. So this is the criteria where which satisfies
A
and tells
wall.
us that it is a wall. And this is the bad minimum that I could come up with without a camera. So this is one of uh, my own logic to find a valid wall. So this is how I find a valid wall. And the next two steps are just move towards the wall until the front range, the frontal reading is less than 0.3 meters, and then align itself to the wall. Basically, the front right laser scanner should actually face the exact point which the robot was facing during this third part. So if it's facing some direction, at the fourth align with the wall case, the robot will make sure that whichever angle heading the robot had, the current front left will have the same heading and will orient itself towards that point. All right, so
Right
yeah,
on.
once the looping stops, it's considered that the service is complete. So the pros and cons of this method is that it finds a wall correctly. But the problem is that it is a little tedious and time consuming, and the algorithm has dead zones where it does not complete and sometimes makes the robot rotate forever. And these are the dead zones. So apparently in this zone, the central red zone, if the robot is started, the service find wall does not complete because the robot goes into a perpetual state of rotation because it's got because the distance of obstacles on all the four sides is like a lot. So we
Mm-hmm.
have the above obstacles and the below obstacles, and when the robot is situated somewhere over here, it has a really hard time identifying which is the shortest distance and which is the valid wall
Right.
because at this point, both the direction of the wall, the walls on left and right seem to be roughly the same distance, and the robot has a problem identifying which wall to choose.
Maybe by
So
reducing
it gets
the.
stuck in a rotation loop forever.
Yeah, yeah, I understand. Maybe by
Yes, what was
reducing
that?
that 120 degree. Well, of
Hmm.
course you have less area
Uh,
to figure it out.
that is true, but the problem is we need to have the 120 degrees is the minimum to actually understand the graph. How do I put it? The design. So if you don't consider 120 degrees, if you lessen it, chances are you're actually facing an obstacle and you're going to move towards it.
Right.
So yeah, that is one of the problems because a valid wall actually follows the smooth curve pattern as you can see over here. It's
Yeah,
like
yeah, yeah.
a necklace or something. So if it doesn't have the smooth curve, it does not identify as a wall. And then the 120 degrees is the bare minimum that I could come up with to have that criteria satisfied.
Right.
And these are the corners are where the robot doesn't make a conclusion. It keeps wavering between the shortest path of either on the left or on the side. So if you take this corner, for instance, if the robot is started from this corner, it keeps getting confused as to which corner to choose, because this is shorter and this is also shorter, but these two
Mm.
are valid walls again. Those are
Mm-hmm.
not obstacles. So the robot keeps uh, uh, wavering between these 2 points as
Trying to
to it
choose,
does
yeah.
not fix itself choosing. Yeah, so the proper way to overcome this is to put a timer there and then end it after like 30 seconds. But the chances are you might probably face the corner and then you will identify that as the valid wall ahead. So that is probably a problem. So these are the dead zones which my algorithm has.
Uh-huh.
And yeah, n- next one is the action. So for action, we just initialize the action server and the goal callback, and we initialize a landmark zone, which is basically the red square that you saw in the image once on the robot done lap diagram. And the odometry, we initialize the odometry subscriber and callback, and then the goal callback does the following task. So it clears the feedback and result variables before the lap starts, and before the robot starts, where we are actually giving like 2.2 and a half seconds of sleep, where the robot doesn't actually do anything, just stops. So that is the time where it finds that the robot is stopped just by checking the linear x and angular z values to be 0,
Mm-hmm.
and then it initializes the landmark zone as that is the starting point. And then it starts running, and it checks for it continues to check for goal preemption, that is if the goal is cancelled or not. And if the goal is not cancelled, assuming the goal is not cancelled and it's continuing, it gets the odometry post for x and y and calculates the distance between the previous and the current odometry values, and it updates the feedback value, which is the current total, the distance that the robot has moved in the lap, and then it just loops over the previous 3 steps until the robot stops at the landmark zone. So once the robot comes to the landmark zone, the action server waits for the robot to stop again. So it continuously keeps checking for the robot's linear x and angular z to be 0. So once they both are 0, and once it is inside the landmark, it is assumed that the robot has stopped inside the landmark and the result is returned. So that is when it is at the landmark zone and the result is returned once the robot is stopped in the landmark zone.
Great.
And the pros of this one is that it records a odometry from a little before the start, not exactly the start, but a little bit prior to the start and a little bit after the finish. So it is actually it's not exactly the lap, but a little bit before the lap starts and a little bit after the lap finishes. So that is a good way to analyze if the lap is complete or not.
Yeah.
And this time it can be tested as opposed to I've already done a ROS1 presentation of the same exact thing, and the only difference with this one is that I was able to create a code that which I can test with or without the wall follower algorithm itself running. So that is one another pro of this method with ROS2. And the cons is that it has nothing, because it is I think it is just the architecture of ROS2 basically as compared to ROS1, and I did not find any cons for this method, so it just worked.
Mm-hmm.
And finally, we have the topics. So this is basically the wall follower algorithm itself. So we initialize the command velocity publisher and the laser scan subscriber for moving and laser recording. And the wall follower is described as follows. So first we look into the obstacle cases. RF is basically the frontal range. So if the range is front
The
is
frontal
greater
what?
than
I'm
zero
sorry?
point 0.5, just basically does a, so yeah, as you can see in this image,
I
RF
see.
is
I
just
see.
the frontal range. So it just follows it just does the wall following logic. And if it's less than zero point 0.5, it takes a hard left. So this is where it faces the corner and it's got a turn. And when RF is less than 0.25, this is where it actually identifies a sudden movement in the arena, like if there's a person coming in or if there's a sudden block that's put in front of the robot suddenly, and it finds, and if the distance is greater than 0.25, it's basically there's nothing in front, so it just continues with the wall following logic. But if it is less than 0.25, that is if it's 250 centimeters, then it turns left until the front is clear, and then it goes back to wall following logic.
I see. Nice.
So this is just the obstacle avoidance that I've incorporated. And now we'll see the wall follower actual algorithm. So this is the extremes. So this shows you what happens if the robot is actually in the zero. away, like way away from the wall or way close to the wall. So this thing is actually, so if the right range is greater than 0.3, which is this line, which is the red line is 0.3, it means that it's way away from the wall. It's too away from the wall. So so if the
Mm-hmm.
front right range, which is this one, is greater than right range is root 2. So this is actually a short formula that it is basically mathematical. So if you look into the measurement of a diagonal of a square, so basically this right range is you can assume this right range to be a square.
Yeah.
So the value of the front right range has to be right range root 2, because it's just basically
A
a
right
formula,
angle.
a theorem for squares or a triangle with two equal sides.
Yeah.
So the hypotenuse has got to be side root 2. So if the right is greater than 0.3 and if the front right is greater than the right side root 2, it means the robot has to turn more right. So it's basically what means that, so we have a right, and then it's like if this line is actually facing more away, so the robot has got to turn this side, which is right side. So it basically turns this side. And if it's less than root 2, it has to turn less right. So in the first case, it just turns right rapidly, and in the second case, it just turns right minimally. And the third case, it just turns right enough so that it stays uh, within the limits and not stray away from the path. And this is the second extreme where the robot is too close to the wall. So it's the same criteria above. As you can see, it's like the front right greater than root 2 of right, front right less than root 2 of right, front right equal to root 2 of right. So if it's greater than the right's root 2, it just turns left. And if it's less than right side's root 2, which is the diagonal value, it turns more left because it's way close to the wall. So it needs
Mm-hmm.
to turn left and go back to the a side which does not have a wall, or go into the path and not get into the wall. And then if it's just equal to the value, it just turns left a little bit just to keep itself within the limits. So this is the extreme condition. Next we see within limits. So this is the case where the robot is within the limits, like within the blue and the red line. So the green line denotes the mean of the minimum and the maximum. So it's basically 0.25. So if the right side is greater than 0.25, and if the front right is greater than side root 2, which is basically the same conditions, greater than, less than, equals. So in this case, we turn right slightly, like slightly in the sense we turn right lesser than the less right over here. So it's just basically
Mm-hmm.
proportions.
Okay.
So it's just hit and trial proportions. So it's just half of this value. So
Right.
more is basically like 1.5 times, less is like 0.5 times, and turn right is like exactly multiple of 1. So if that is 0.5, this slightly is like 0.25 times, is like half of the less. So just very slightly.
So
And then
mostly it will
if it's
be.
equal to, we just want to keep it in track. Sorry, what is that?
So mostly it will be within limits. That's what you mean.
Exactly.
Okay.
Exactly. So we're just trying to keep the robot well within the limit and not stray away, because it causes a curvilinear line as opposed to a linear line. So we
Right.
want to avoid that, because this is a wall follower and it's not supposed to go like dancing around, if you understand what I mean.
Right.
So
Yeah.
we don't want it to stray away and go in a snake-like path. So we just want to avoid that. So in this third case, it's like well within the limits, and it's doing its job. So we are just barely moving it right. It's like very small. It's like 0.01 or something. So yeah, that is what this does, and this is the exact opposite of this one. So if it's less than 0.25, that is if it's over here, we just do the opposite. So we turn left very small in this case, and then we just basically do the same thing over here. So we're just keeping the robot within the limits, and we're just not letting it stray away once it comes into the limits. So that's pretty much for the wall follower. And to analyze the output of the results of wall follower, the pros are it properly utilizes the scan gratings to follow the wall. It avoids sharp turns in the corner because we have set it that way. And the only problem is that due to continuous scan and move method, like you scan, move, and you do not stop in between, So because of that way of design, the robot actually follows a non-linear, actually a slightly curvy path, as opposed to a straight linear path. So that is something that is not avoidable. So that is something you need to watch out for. So
Right.
yeah, unless you're considering a lot of conditions to make the robot move, if you just want to barely get it done with like 3 or 4 sensor readings, this is something that you need to overcome.
Mm-hmm.
So this is one of the cons of my design. And now for all the parts combined. So since ROS2 has a callback based process as opposed to ROS1, which contains like you can actually in ROS1 you can actually put a snippet of code anywhere and it will just run fine. But in case of ROS2, you just need to make sure that the program snippet that you put in there is actually falling within the callback, because the main running function in ROS2 is basically the timer callback, which you provide uh, for the robot's movement or something. So you do not want to mess up in that callback. So so this in this design, this is actually way different from my previous design which I had in POS one,
Mm-hmm.
although the logic is pretty much similar. So you initialize the publisher, subscribers, sales clients, and action clients in the combined logic, which is the main program. You find the wall and then orient it next to it and start the wall follower algorithm. And once you're about to start the wall follower algorithm, you call the callback, which is the main function, which is the timer callback,
Timer.
which you refer to in ROS2. So what it does is we have a lot of flags to determine the state the robot is in. So we have, if not pre-ready, this is one of the conditions. If it's not pre-ready, we call the find wall service and make sure that the robot is orienting itself. So once we start we set pre once if it's not pre-ready, we call the service and set pre-ready to be true. And next case, if it's not ready, and if the wall is not found, we wait for the service to complete. And if the wall is found, we initialize the landmark zone, we send the action goal, that is to start the action server, and then we set ready equals true. And then we skip to start it. So if it's not started, we note the start time. That's basically it. And then we set started to true. And then if it's not running, so initially the running is set to false. So if it's not running, and if the robot is inside the landmark, we perform the wall follower logic and keep checking for the robot reaching the landmark zone or not. So that is a check for landmark. And if it's not inside the landmark, we just wait for the wall follower logic to finish,
Right.
and then we set running equals true. And we have another flag which says which is finished. So if it's not finished, we have two conditions. If it's not inside the landmark, we continue with the wall following logic and then keep checking for the landmark. And if it's inside the landmark, we start checking the distance to the landmark. So this is where we check the if the robot has reached once the robot has reached inside the landmark. This is where we check the distance between the robot and the starting point is actually less. So this is where the calculation for stopping comes into play. When the distance is lesser is the least, the next point is going to be the stop point. So this is where it happens. And then we mark it as completed, and then we finish, and then we note the finish time and then set finished as true. And this is the final point. So before we report, we have the not pre-report. So we wait for action server to send the results because the robot is now stopped. And then once the result is obtained, so this time we check for not reported, and then we just print and save the action result and the lab statistics into a file, and then we just reset all the Boolean flags once all the flags are complete. So this is basically the callback which does the run. So this goes over and over again once the lab completes. So
Right.
it's a continuous process. And these are as you already saw, these are some examples of my run. So in this case, you actually see this is a Python run. So in this case, you actually see that the starting point and stopping point are very close. This is in this specific case. So it had a good run. And in this case, as you can see, it is well within the landmark zone, but it's a little bit away from the starting point because that's the closest it can get to the starting point because of the path difference. Because
Mm-hmm.
the robot did not take a path like this, but it took a path like this. And these are the two examples. And yes, finally, debugging with ROS2. The only thing I found with ROS2 is that there is no Architect console like you had in ROS1. So
Unfortunately.
the easy way to debug ROS2 program is using ROS2. What was that?
Yeah, I said unfortunately.
Yeah, because yeah, you can still use RQT console, but if only if the robot is using if the robot is running on ROS1 and you have somehow bridged the ROS1 function to ROS2. So that way you could probably check a few of the debug messages, but if it's completely ROS2, then chances are you cannot use RQT console. So this is your only bet. And some explanations, I've already explained this. So this is basically why the lab may not start and stop at the same place. I've already explained you that, so I'm just going to skip on that.
Yeah.
And yeah, areas to improve. We have the wall follower algorithm seem to have, we need to have more linear movements than the curvy movements. So as you can see in these two designs, we have a lot of linear movement over here, but as in this graph you can see a curvier movement as
Yeah.
opposed to be it being straight. So and this is more clear because this is taking a curvy path, and we want it to be as straight as possible. So that is one of the tasks that should be improved. And service, this is the wall follow finding wall service. So I need to find a way to improve that by uh, reducing the time it takes to find a wall. And action is actually for the action, it needs to have a better way to perceive the lab completion without the sleep because my current design actually depends upon the robot coming inside the landmark and sleeping for the 2.5 seconds. So I need to find a way to overcome that and yeah, not depend on the sleep because that is one of the other ways, as we saw earlier in this video, that the robot prematurely, like the action server stops prematurely. So I
Yeah.
need to find a way to fix that. So that is one of the areas to improve. And then I got to use the IMU for better robot positioning and
Oh.
more precise distance covered and average speed statistic calculations.
Yeah.
And that's pretty much the areas to improve. And one another minor thing would be to improve more, to add more commenting into my code, which is basically something we
Everyone
can do
has that
later.
problem.
Yep,
All right.
this is one of uh, my analysis using ROS1 and ROS2. So these are my first sight differences. It may or may not be true, but this is what I found to be happening. So these are my opinions and views on those. So comparing ROS1 and ROS2, ROS1 is basically not structured around callbacks, but ROS2 is mostly everything is like structured around callbacks. So you got to be careful with that. ROS1 is easy to program, but it's quite tedious to debug, which is in my opinion. But ROS2 is actually tedious to program because of callbacks, but it's easy to debug. And I do not know why I found that to be true, but it's just in my case.
Mm-hmm.
And ROS1, in ROS1, as I said earlier, I can actually add a code snippet anywhere, and you don't have to worry about it executing or not. But in case of ROS2, you must be careful of the callback functions because if you put it somewhere, and it's gonna take a it's if it's a forever while loop, and you get stuck in a callback, it's gonna keep switching over and over again, and you'll probably face a lot of problems with the program or the algorithm not completing or getting stuck forever. So that is one of the things to look out for. And in ROS1, I actually also found that the nodes are standalone classes as opposed to ROS2, which actually gets inherited from a basic node class, like sub base class of node class. And then in ROS1, I could have more than two subscribers in one program without using multiple threads. And in ROS2, I have to use
Yes.
multi-threaded executor
Yes.
because that's the only way to get subscriber callbacks running in parallel with ROS2. So overall, my analysis is that ROS2 seems to be easier for me to work with than ROS1. It's just my view. I'm not sure how others find, but since ROS2 is getting popular now, we probably need to make that change and
Yeah,
start
it's
understanding
a hot
ROS2
topic,
better.
which one to use, and um, I'm with you, especially since we are getting
Yeah,
close to the. I mean, they're not doing any more ROS one releases, so I think it's
true.
important to start thinking ROS two and everything.
Yep,
Um,
yep.
and
I totally agree with that. Yep.
unless you have a huge system that it would take a year for you to switch, then you can think about things like the ROS bridge and things like that. But you're
Mm-hmm.
I mostly agree with your comparison here. Um, so
All
Great.
right. So I guess we have reached the end of our presentation, and that's pretty much all what I have to show.
Awesome.
So, yep,
Well,
I'm gonna
great
close
job,
this.
Girish. Do you mind
So,
stopping sharing your screen so we can just look at each other?
yep. All right.
All
So
right.
stop sharing.
Here we go.
All right. So my camera is not working, I believe.
Oh, don't worry.
Stop video. Start. All right. There we go.
Nice.
All
Okay,
right. Hey,
so
that was a good run for both Python and C++. Didn't
yes,
expect
yes, it, it,
that to
w- it
go
went really
this
well.
well.
Yeah, yeah. So congratulations. Really,
Yep.
really complete project again. And
Thank you so much.
let me ask you some
Hmm.
questions. We got like 5 minutes, so let me ask you some questions and comments that I think are
Sure.
interesting. So one thing,
Hmm.
what bridge did you use? The dynamic or the parameter bridge? Or you don't remember?
I use a parameter bridge.
Okay, so that would reduce things because you select the topics. That's nice because the
Hmm.
dynamic bridge just seems to go way slow. So maybe I thought, oh, maybe that's one of the issues with that action server thing. All right,
True.
then yes, I
The,
believe
the,
that
the
stop.
parameter bridge actually provides the exact topics that you want, like the odom, scan, and command velocity. You don't need more than that for
Yeah,
the robot to actually
NTF,
move.
I think.
I would have included the camera, but it, I didn't feel like much use for it. So
No, no,
yeah,
and
because I'm not going to use the camera other than just to view what the robot is seeing.
exactly.
So I did not feel like improving it. And yeah.
And this leads me to the other part, which most of the times
Hmm.
you're gonna be limited sensor wise. So most of the
True.
times you're gonna have cases where you only have that lidar, let's say, and I'm still really
True.
impressed by your algorithm to determine whether or not to wall with the use of mean and standard deviations. It's very important
Hmm. Hmm.
with a lidar, and think about it. You can use this as a base to do the opposite, which is to find an obstacle. So, for example,
True.
an obstacle can be a charger, go towards the charger,
Hmm.
right?
Hmm.
So this base that you've worked on, you can literally expand it to, recognizing feet, recognizing only by
Hmm.
the analyzing of the means of standard deviations, you can find a path of figuring
True.
out how to determine what 10 things, so that's a great thing um,
Hmm.
to have. For example,
Although I should still improve my statistical reasoning and
oh
algorithms
yeah, but
because it's not exactly functioning well. So I gotta still improve on that
okay,
function.
okay, yeah,
But yeah,
but
that's actually a simple and easy metric to easily fix on a valid wall. So
right,
that's like a faster method.
yeah, yeah,
It
yeah,
We should find a method faster than that and then less computationally expensive.
right, that's true. And but yeah, I wanted to say to keep that in your files because you might need it again
Hmm.
and later. So um, another thing, you talked about the need to have less curvy paths, and this is not part of the
Yep.
course. And I noticed
Hmm.
because your controller is great because it has. You were talking about, we can just have two conditions and have it go like zigzag, and that's fine. And
True.
so,
True.
so you have the extremes, you have the normal functioning, you have all of these types of conditions, which I'm assuming they translate to
Hmm.
if and else in your code. And
True,
so,
true. It's like a lot of bunch of if and else. It's like
right,
12 if and else.
right,
But
right.
if we are using like a lot of if and else, we just want to make sure that the conditions are short because we don't want to have every if and else statement checking for like a bunch of conditions. Like 5 or 10 is like really
Yeah.
weird.
And this is
Yeah, we just want to make sure that the processing time to actually understand the conditions in a if code in an if statement does not exceed the time it takes to make the decision in that
right.
if statement.
Yes. And um, so instead of this, you can start looking at
Mm-hmm.
implementing like a simple PD controller just for the
Mm-hmm.
straightaway section, for example. And there are a bunch of examples I can share with you later, because this is not part of the course. But we
True,
have
true,
there's a really
true,
simple
true.
way to
Yep.
do a PD controller, and you're looking at the error.
Mm-hmm.
For example, here you would look at the error of the right side,
Mm-hmm.
and
Mm-hmm.
every time your timer callback, which I think that was the frequency of a timer callback, and that's why it was, you know, just stop
Yeah,
it,
that's
go
true.
and
Yep.
stop it.
It was having a jerk and
Right.
in a like
So,
stop and start move. Yep.
so you increase that timer callback, and then you put that PD controller. You should be able to see how it's just controlling much better. And
Mm-hmm.
I think once you get the hang of it, at least for the simple cases, it's a lot easier than trying to figure out every single condition. So I think uh, that would be
True.
a great thing to have. But again, it's not part of the course. But
On a side note, I did think of implementing an adaptive speed control, like reducing it step by step, as opposed to having a fixed speed for the turns and movement. But
right,
that didn't seem to work out well, so
what? Yeah,
I
you fix
basically
this with
didn't do
a
that.
PD controller. So for example, with PD controller,
Hmm.
you control the angular velocity, so that will change, and the amount
True,
and
true.
the
Hmm.
direction. But and then for example, you set fix the x direction, so it will continue to go forward, but then only measure that, and it works really well. I've implemented one for like
Yep.
auto charging, and it works really well every time. So that's another
Hmm.
thing.
Hmm.
And I mean, the last thing that I wanted to just mention, because we're out of time, is that's a really
Hmm.
interesting thing that you told me about that lag. That's possibly because of Python going to C++ and into the
Yep.
robot.
Hmm.
And it's curious to me that it happens in the action server. So one good idea to try
Hmm.
would be to see if this happens with a service server that does the same as the action server,
Hmm.
right? But you don't get feedback. That's the only
True,
difference.
true.
So
Hmm. Hmm.
I'm interested in this, so I will go into it and see if this is an actual issue for fact that you're using Python, or like even
Hmm.
something weird with the action client in ROS2. But that was really, really interesting because I saw you killing it and launch it, killing it and launch it.
Yep.
Uh, so that
Yep.
means something's
It's
up.
it's just yeah, it just doesn't seem to respond at some places when I'm using Python. I think Python converts it into C rather than C++ because
Oh, okay.
Python, I think it uses Cython, which is basically
Yes, I thought.
converting down to C. So yeah, I think it converts down to C as opposed to C++.
Yeah, so that would be interesting. I'll keep an eye out, and uh, we'll continue to investigate that. But anyways, other than that, I thought it was a perfect project. Great job, Girish. You presented two
Thank you so much.
courses in one go, so congratulations for that. And
Yep.
for everyone else that is watching, you can do this and
Hmm.
apply your knowledge here in the courses you take, and do it in a really like laid back way, so you can show people that you actually learn in the courses we offer. So everyone is invited to do what Girish did here, and that's it for me.
Yep.
Girish, thank you so much for
And
your
actually,
yes.
an addition to note for all you viewers, I believe that the construct is the only place where you can actually find a lot of programs. I mean, a lot of courses on ROS1 and ROS2 as opposed to places like EDX and Coursera right now, like during the take of this video. So I couldn't find a place where I could find ROS2 courses. So this is the only place at the moment, like you can find ROS2 courses. So make use of it, people. Like,
Oh,
don't let
love
this
that.
go as a waste.
Love
Like,
that. Love
discover
that.
this place. You have a lot of courses to learn. You can really improve your robotics.
Yes, we do. And overall, like, you know, critical thinking and programming, because uh, programming is
Hmm.
good for everything. It's good for doing statistical analysis,
True,
like
true.
here Girish did. So, Yeah,
Mm-hmm. Mm-hmm.
come take a look at our courses, guys. All right. Um,
Yep, definitely. Yep,
well, thank you, Girish. We'll see you next time, and thank you.
yep. Thank you so much for your time also.
All right. Bye bye, everyone.
Bye bye. Bye bye.
Okay, cool. I ended